Hi, welcome back. So today we will again revisit the concepts of range, domain and codomain and do some challenging problems as we had discussed last time. When we are doing these problems, we'll realize that like functions have a lot of concepts that need to be understood in order to even figure out domain and range for a function. So we will look into examples of we will look at some examples of functions which are very commonly observed, and then we would go into some algebra of functions. So let's begin with some very interesting examples of figuring out range and domain for a function. So an interesting way to figure out range and domain, as we had even seen last time for simple function, is through visual inspection. So let's say if you're given a function, you can draw the graph of that function, and based on that graph you can determine the range and domain of that function. So let's take a function for which we are already given a graph. Now if a function's graph is given, let me use a different color to draw the graph. So let's say this is a function for which we know the graph. So how do we determine its domain and range? So a very intuitive way to determine the domain of a function is to first we have to ensure if this plot includes all of the function. So let's say here we only see the positive real axis and the positive axis on the y side. And if for instance like there were some points on this function which were not in this area and which were not shown in this graph, then we cannot say the domain and range. So for functions whose whole graph is not given, we cannot through visual inspection figure out what the domain and range is. But let's say this is the overall function that somebody has given to us, and the person who gave us this function told that this is the complete function, and now you want to figure out what is the domain and range. So the simplest thing is view the function from top and see which points on the x-axis are sort of hidden. So if I see it from the top, all these points are hidden. So all the points on the x-axis which are hidden are the points which lie in the domain of the function. And similarly, if you want to find out the range, look at it from this direction and see all the points on y-axis which are hidden or which are covered, and they will form the range of the function. And so this is a very easy way to figure out domain and range of a function if the plot is given, or if you know how to draw the plot of a function. But as I was saying, if a function for which let's say you don't know the complete graph, so let's say somebody draws a function like this and doesn't tell you what happens afterwards, it's not possible to figure out just from this graph what is the range and domain of that function. So next, let's look at some examples where equations are involved. So oftentimes functions needn't be defined completely. So let's say, so this is a very important problem. So let's say you have two functions, f1 of x and f2 of x, and you know the domain for f1 of x is d1 and domain of f2 of x is d2. So remember, domains are sets. So like union of these three intervals is a set. So that's the domain of this function. Presumably the whole real axis might be the domain of this function. And now we are given that there are two functions which we don't know, but they are just labeled as f1 of x and f2 of x, and each of their domain is d1 and d2. So now for these two functions, how do you determine what's their domain? What is their domain? So let's say we have a function which is dependent on these two functions. Let's call this f3 of x, which is given by f1 of x plus f2 of x. And now you want to find out the domain of this function. So let's think of some examples. So let's say f1 of x has domain D1, which is already given, and f2 of x has domain D2, which is already given. And let's just for our thinking, assume that D1 has this elements a, comma b, comma c. So D1 can be anything based on the descriptions that has been provided to us. But for our thinking, to figure out what the solution should be, we just assume D1 is a, comma b, comma c, and D2 is c, comma d, comma e. So based on these D1s and based on this D1 and D2, what can we say about domain of F3? So clearly, C is in domain of F3, because for an element to be in the domain, it should be defined for both F1 and F2. But A, B, and D, E are not in the domain, because F1 of A exists, but F2 of A does not exist. So from this simple example, we realize that for a function, for the sum of two functions, the domain of function is actually smaller than the domain of each two, or can be smaller than the domain of each two. And this was just an example that we took, but D1 and D2 can be anything. So this can be anything. Similarly, this can be anything. So what essentially we did was we saw D1, we saw D2, and found the common elements. And if you remember from sets, common element of two sets are given just by their intersection, which is denoted by this symbol. So if two functions are being added, then the domain of the resulting function is just the intersection of D1 and D2. So this was an artificial example through which we solve this problem, and that is often a nice way to try to tackle some problems, because you can try to solve the problem in its generality, or try to take some example and see what happens in those examples, and from that come up with a general rule. So this is an important property which you should remember, not just for this question that we solved, but for in general. And in today's lecture, we would see something which involves algebra of functions, and this is essentially addition of two functions, and for that we know what happens to the domain. So similarly, let's say if we have, instead of addition of functions, if we have division of these two functions. So let's say we have a new function, let's say f4 of x, which is f1 of x divided by f2 of x. And again we try to take an example and try to solve for that. So let's say f1 of x is log of x, and f2 of x is x. So first we need to think, first we need to figure out what is the domain D1 and D2 for each of these functions. So D1 is positive reals, so which is equal to x such that x greater than 0, and D2 is all real numbers. Now clearly, if we see what f4 of x is using these two definitions, so in this case f4 of x is log of x upon x. Clearly, if x is negative, the numerator isn't defined. So this rule still holds, that like for an element to be in the domain of the resulting functions, which is obtained by division of one function by the other, the element should lie in the domain of both. So perhaps one solution is d of 4 is d1 intersection d2. But as you can notice, we also have a denominator. So we have to make sure that denominator is not equal to 0. So this is actually not the correct solution. In addition, we need to make sure that the denominator is not 0. So D4 is actually a subset of D1 intersection D2 without the elements where F2, the denominator, is 0. So in this case, it is simply D4 of x is simply all positive zeros, all positive reals. And here what happened was x was the denominator was 0 only at 0. So D4 is essentially a D1 intersection D2. So here we saw two simple operations on functions. So one was the addition operations and one was the division operation. And here we saw that like the function wasn't defined explicitly, but it was just given in terms of symbols, and from there we tried to take some examples and come up with what happens to the domain for these functions.